Yeah. So I'm just keeping it on the screen where I left you the last class, right? So a quick recap of what we did. In the last class, we primarily focused on the extension of the spline representation that we had seen earlier to represent curves whose shape are known to you already. You know, their shapes are already defined in an analytical form, and yet you want a representation for the same. Close this. So you want to be able to represent them. I think I don't have slides for this set. I'll make some at some point. So you have a known curve here. In this case, it's an arc of a circle subtending 90 degrees at the center of the circle. And we showed first that, you know, the regular spline that we talked about earlier cannot represent this arc of a circle, because the form that we need, the parametric form that we need, is actually a ratio of polynomials. And therefore, we define a new curve, though it is not actually new, because the basis functions are still the same. There is only one addition of this weight associated with each control point, and a term on the numerator, which is the weight of the weighted function, sum of the basis functions. But the basis functions are the same as the spline functions, and therefore we call this the rational B-spline, right? We call this form the rational B-spline. And then we showed that you can actually then pick these weights on these control points to pretty much achieve any shape that you want. And the significance of the weights, we saw that through an example, right? That the significance of the weights is that as the weight increases corresponding to a control point, in this case, say P1, right? The curve starts to be pulled towards the control point. So as H1 is 0, the curve is the farthest away from this point. And as H1 increases, it gets pulled towards the control point. And of course, the academic point is that for the asymptotic value of infinity, right, where H1 approaches infinity, the curve actually passes through the point P1. Okay. And like I said, that the solution that you get for a given curve with the rational spline is not unique. We earlier showed that a weight of 1, 1, and 2 associated with each will be enough to define the curve. But then we also showed later that a symmetric set of weights, 1 cos theta 1, will also represent the arc of a circle. And the distinction being that in one case, the tracing of the points on the curve is uniform as the speed with which the parametric space, we move in the parametric space. So if we reach 0.5 in the parametric space, we would reach the midpoint of the curve and so forth. Whereas with the 1, 1, 2 set weights that we had calculated, you will get an arc of a circle, but there will be a mismatch in the speed with which you traverse in the parametric space and the speed with which you traverse in the real space. Okay, so that's the only difference. I did leave you with a question. So before I go back to that question, let me just ask you if you have any questions or comments that I can respond to. Yes, please. Okay. Yeah, somebody?
Sir?
Yeah.
I have seen confusion on the value of h, how the h we have putting in this type of curve, the nubs.
Okay. So there is two things that we have done here, two curves we actually obtained. And let me just go to both of them. The first one, I lost my mouse. Yeah, here it is. See, the first one, where is it? Here. Right, the one in blue in this middle of all this text in green. Right, so if you see this here, right, if you see the box that I'm drawing now, right, so this is one quadratic rational B-spline curve on the left-hand side. Okay, so for a given set of control points, 1, 0, 1, 1, 0, 1. This is something that we had obtained from just what we know about the spline curves. and we stayed with the same. And the only thing I have done around that is to write down the rational spline expression. So I have weights associated with each of the control points, H0, H1, H2, and then the basis functions, the quadratic basis functions is all I have written. And the denominator term here, right? And this I equate to my representation of a circle, right? Which is x coordinate is 1 minus u square by 1 plus u square, and the y coordinate is 2u by 1 plus u square. This comes from coordinate geometry, right? You know the form cos u and sin u. So imagine u to be, cos u to be written in terms of tan u by 2, and you will get an expression like this. And sine written in terms of tan theta by 2 or tan u by 2 will result in an expression like this. Okay. So what we now say is that I have an expression for a rational spline here, which is supposed to represent the arc of a circle. I have the exact representation of the arc of a circle here. And so both must be identical for all values of u going from 0 to 1. Right? So in this expression, if you see, the only unknowns that you have are the h0, h1, and h2. Right? Because it has to be true for all u, I don't worry about this. The control points are given. So all I have to do is match coefficients of u on either side. So for the x coordinate, as I said, I get this set of terms added to be equal to 1 minus u square. For the y coordinate, I get this set of terms added to get to u, and the denominator to get to 1 plus u square. And this must be true, equal. All three equations must be satisfied for all values of u. So the only thing I need to do then is pick the constant terms and equate it to 1 here, pick the coefficients of u square and equate it to -1, pick the coefficients of u and equate it to 0, right? So like that, I will get equations, and I solve those equations, I get these set of values. So you're not picking them here, you are actually solving for them. Okay, in this instance, right? You actually solve for these. But the other example that we showed, right, the one here, this is somewhat different. Here, I did pick values for h, but only for 2 of the control points, the first and the last, in the case of the quadratic curve, right? h01 and h21, and we left this as an unknown, right? And then later, we sort of stated, I did not show you how, but I just stated it, that different values of h1 will result in different types of conic sections. h1 equals 1 will give us a parabola, h1 greater than 1 will give us a hyperbola, and h1 less than 1 will give us an ellipse. Right? I admit that we have not proved it because it is beyond the scope of this class, but that's a fact, right? And since circle is a special class or a special form of the ellipse, you know that there will be one particular value of h1 less than 1, which will give us a circle, and indeed it is, right? So if I'm looking at h1 value of cos theta, it will give me an arc of a circle that subtends an angle of theta at the center. Okay, so if I take this figure, right? So imagine if I name it the same way that we have named it there. So this is P0, P1, and P2. So this is the picture, but the angle subtended at the center is 90 degrees. And therefore, if I choose h1 to be equal to cos of 45 degrees, half of that, then that set of weights with this set of control points will give me an exact circle. So here again, I have not calculated it, strictly speaking. I calculated it once, but I have a formula now, which means that 1 cos theta 1 will always give me an arc of a circle which subtends an angle of theta. Now, if your question is, what about other types of curves, right? Now there, it is a little bit of a tricky situation. The tricky situation is mainly because we, in practice, that is when you are actually sitting in front of a CAD system and modeling curves, we very rarely use HIs. So by default, HIs are always set equal to 1. So for every control point, right, in your CAD system, when you're sitting in front and designing arbitrary curves, etc., the default value is always 1. It's only when you pick this option of a circle, an ellipse, a parabola, or even a hyperbola that it will choose the option of a rational curve. Okay, so in some sense, you actually, if you look at the set of parameters that we had said, K, NPI, right? And the type of knot vector. We don't have to find the knot vector, but we have to specify the knot vector. But this, by default, is always set to be the open uniform, the one that we described, right? The first k is 0, the last k n minus k plus 2. So this is always fixed in the CAD environment, right? These are three things that you pick. And for most curves, this is already frozen, right? You don't get to change this, right? Except when it is circle, then, it works with this. And for ellipse and other things, it'll, find it through other means. Okay, so the sort of after all this explanation, the answer to your question is that for circles, the known curves or ellipses, right? Yes, you have to choose h, but not all h's, only the h1 in between, because this is the preferred form, symmetric, 1 cos theta 1, right? Or 1 h1 1, sorry. For all other curves, we very rarely, as in CAD systems, never, we will be allowed to tweak the HI corresponding to that. Okay. There are research papers which will tell you what advantages you get when you also allow the user to pick HI, but in CAD systems, it never happens. I don't know if that doesn't answer your question. I'm sorry, yes, I went about it in a long way, but I hope that made things clear. Yeah.
Yes, it's clear now.
Thanks.
Thank you.
Okay. Any other points or questions? Okay. If there are no other questions, then let me go back to my question, which I left with you at the end of the last class, which is that I said that now you know how to define an arc of a circle which subtends an angle theta, right, at the center, right? And so I drew one arc of a circle which subtends an angle of 180 at the center. And my question to you was to tell me the representation of this arc. So do we have an answer now? Okay. I'm assuming that silence means no answer. So let me then throw one possibility at you, right? So let me just draw it clean and lower this screen a bit. So the question is that I have an arc of a circle, right? Maybe that doesn't look like an arc of a circle to you, but believe me, or imagine that it's an arc of a circle centered at the origin, right? And so the angle subtended is 180 degrees, right? So that's also known to you. You know two things, which is the endpoint P0 and the other endpoint. And I'm going to call this 2 right now because I'm going to assume that because we are interested in a quadratic Bezier, right, or a quadratic curve, I can get away with the smallest. So K still remains what it was earlier. K is 3. And therefore, we said that the smallest value of n that you can start with is what? 2, right? So that n plus 1 is equal to K. And so you get a single segment, which is this curve, right? So we are, proceeding the same way that we did for the quadrant of a circle, except that now we know that P1 has to lie somewhere on this line and P1 has to lie somewhere on this line. And then, we have a problem, right? Because there is no practical way in which you can allow P1 to be infinity, which is what this is saying, right? Because it is way out there. They are not going to intersect at all, right? So what do we do? So do we admit then that we cannot represent a curve which is beyond 179 point whatever? Or do we have a solution for this? Any thoughts?
So by increasing the control points.
By increasing the control points. Very good. That is indeed a solution. Okay. So the suggestion is that, yes, indeed, I cannot do this with n is equal to 2. So I need to up the number of control points. So what is your pick? Since you have given the answer, what do you want n to be? 3? So which means I have 4 control points, right? Does that help? So I have, maybe I pick 1 point here and 1 point here, and that becomes my control polygon. Is that the solution you want?
No, so that is n to 4, like 4 control points.
Yeah, so that is because n is 3, no? So I have 4 control points.
Yes.
So this becomes P3, and this is P1 and P2. But do we know whether this will be an exact circle or not now?
No, sir. Like we need one H parameter to define the curves.
Yes. So this, as we said, was 1. And assume we started this also with 1, but now we need to assign values for this. So we have an issue here that, of course, if your idea is that by controlling H1, I can sort of solve this problem, it's not entirely correct because you still will have to locate these points correctly, right? I don't know if we have still done that. So I like this thing that n is 3, so we will keep that. But I want to pop this question back to you again to say that is there something more definitive you can tell me about P1? Because right now also we have not frozen P1 at all, or P2.
Yes, sir. Like we can introduce one more point like between, like the point is defined since it's center and the radius is unit 1. So that will be one more defined control.
Let me draw that picture here separately. So again, a horrible looking semicircle, and that's the center. So I have P0, which is, let's say, as you said, I know the radius, so this is 1, 0, and I mark this as P1. This is 1, 1, right? And same ways here, I might have a -1, 0, and I mark this point here, which will be -1, 1. Okay. So what that will do for you is that. Right? That becomes your control polygon now.
Yes.
If you choose this. And let's say for H1, H0 is 1. Sorry, 1 second. I'll just write this and then I'll come back to you. Yeah, go ahead. Tell me now. Somebody was saying, want to say something. Go ahead.
Yes, sir. Go ahead. Okay.
So the suggestion was that we pick points that we know, and because we know that it is arc of a circle, and so we sort of went back to the same kind of a construct that we did for the quadrant and picked this point exactly at 1, 1, and this point exactly as -1, 1, and so that becomes my control polygon. Is there anything still predictable that we have here? Can you confidently say what the weights should be for P1 and P2 here? So this is P3, and I need an H3 for this.
Yes.
So what does this picture? Yeah, go ahead.
Yes, sir. One more point at the middle.
One more point is needed.
Yes, right, perpendicular to the center. Yes, sir. That's
right there. Okay, fine. So I'm going to label this as P2. Now I'm going to cross this and label this as P3, and I'm going to cross this and label this as P4. Okay. Now, what does P0, P1, P2 give you? What does it remind you of? It's the same configuration as you saw in the earlier example that we did, right? A quadrant of a circle subtending 90 degrees. If that is the case, what should H1 and H2B. Right? If these 3 points have to define for me this quadrant of a circle, right, 1/2 of the semicircle, then these must be the values of the weight. We have already seen that. Right? So that takes care of this. And by the same argument, if I flip the picture that I drew in the earlier class above about the y-axis, then I get this picture here. And again, I know that this must be equal to 1/√2, and this must be equal to 1. And then these 3 points will give me this arc of a circle. And therefore, I have my full semicircle here. Correct?
Yes.
Do you buy this? That we have basically tried to represent the semicircle, not by, some single entity like we tried earlier, but as 2 segments. One segment which is a quadrant, 90-degree arc of a circle, for which I have already calculated the control points and the weights, so I know what these are. And I just use the same, but for the next set of control points for the semicircle that I derived, and this gives me this part of the semicircle, and put together, I get the whole semicircle. Correct? Now, the nice thing about this idea is that I can extend this like this. So this is P4. So I have P5 and P6, and I'm going to write H1, H values below that. H5 is 1/√2, H6 is equal to 1. Right? So then again, I have 1/√2, 1, and therefore this will also represent a circle arc. Represent an arc of a circle, which is drawn in blue here, right? And again, I have one more point here. I call this P7, and I call this P8, which is the same as P0. And I attach this weight here as 1/√2. So I have another set of 3 control points, right, with weights 1, 1/√2, and 1. Therefore, this will define this quadrant of the circle. And so with this now, I have the set of control points and the weights to define the complete circle or arc of semicircle. Does this make sense to everybody? Does everybody think that now we have a representation for the entire circle?
Yes.
A quick yes or no?
Yes, sir.
Okay. Is there anybody who thinks no? Okay, so I'm assuming that we have unanimity. So now what I'm going to do is I'm going to write down the parameters and the inputs that we have given. So P0, P1, P2, P3, P4, P5, P6, P7, P8. Note that I need the P8. In terms of location, it is the same as P0, but I do need this control point, right? There is a P8 because I need them in triplets. P0, P1, P2, then P2, P3, P4, then P4, P5, P6, and then P6, P7, P8, right? So I do need a P8. It just so happens that its location is same as P0, and therefore I will get this closed curve. I have the set of weights. Associated with that, right? So that gives me the circle. We have already taken K was 3 and N in this case is 8. I have 9 points here, right? So does this look right to all of you? Again, a quick yes or a no.
There are too many control points.
Too many control points. So where would it hurt us?
Like making the equation.
Well, you're worried about computation.
Yes.
Well, okay. You think of it like this. The computation is still very simple. right? You just have those recursive relations, right? You just have to do them over and over again. The computer will do that. It is not complicated, but it is effort. And there is a difference. Okay, and we will see the nuance of the difference later. But what I'm trying to say is that all you need to do repeatedly, even just because you have many control points, is the computation of the basis functions, which has this form k minus 1 plus something and I plus 1 k minus 1, right? But you do this. It's a very simple calculation because there is some difference here, and then some value to be taken from the previous step and added and multiplied and added, and that's it. And you do this over and over again. So while you do have to do it a lot number of times, it is not complicated. The reason I'm mentioning this point is that this is not the same as increasing the degree of the curve. See, when you increase the degree of the curve, the computation itself becomes more complex, right? That's why I'm making this distinction. But point is taken because the issue is because of the points, but the issue is not what you pointed out. Okay, so let me just give it a shot now, right? So X corresponding to this particular combination, right? If I insist on the open uniform knot vector, right? So we have said that by default, you'll always get the open uniform knot vector, which means the first k elements are 0 and the last k elements are n minus k plus 2. So this is 8 minus 3 is 5 plus 2 is 7, 7, 7. And in between I get 1, 2, 3, 4, 5, 6. Right? So 3 plus 3 plus 3 plus 3. Yeah. So now I hope you start to see that we are having a problem now. What does this number 7 signify? N minus k plus 2. It says that I must have that many segments in my curve. Right? How many segments do I have in this curve? How many segments do I want in this curve? Sorry. Let me put it this way. You want 1, 2, 3, and 4. That's all you want. This is actually going to give you 7 segments. Right? And therefore, there is a problem now. Right? While on paper, by assembling these 4 quadrants of a circle, which we know how to define, I can assemble the representation for the circle. But for me to get a single spline-like representation where each segment is this arc of a circle, this combination doesn't seem right because this says that I must have 7 segments, whereas I only want 4 segments. Okay, so let me put one more sort of picture in front of you. Right, so the first segment is defined by P0, P1, P2. The second by P1, P2, P3. Third by P2, P3, P4. The fourth by P3, P4, P5. Okay. So those are the segments that we have. K control points define each segment. So I start from the first and start writing the K tuples. In this case, it is triples. So P0, P1, P2, P1, P2, P3, and so forth. But I keep toggling between top and bottom because if you see it this way now, you will appreciate that in my curve that I want to represent, I want the bottom triplets, right? P0, P1, P2, P2, P3, P4, P4, P5, P6, and P6, P7, P8. But I don't want the top ones. Right? Because those are not of, I don't want them in my curve. That's not of interest to me at all. Right? So let me also do the same here. The first segment triplet is 0 to 1, second, third, fourth, fifth, sixth, and seventh. Right, and again, you want these segments to contribute to your shape, but you don't want these segments to do anything for your shape. So how do I get rid of this problem that we have gotten into now, that I'm getting some additional segments that I want to do without? So what I'm saying is that if you were to actually take these inputs and feed it into a program that generates the spline, you will not get the circle back. Right? Even though triplets of them will give me quadrants which put together will give me the circle. So the only way I fix this problem is to try and get rid of these segments. And how do I do that? And this is probably a little jump of faith, but I hope I can give you a physical feel for that. I define a new knot vector which looks like this. Okay, now it satisfies the definition of the knot vector. There are n plus k plus 1 elements, right? X goes from x naught to x n plus k, right? And it is non-decreasing, right? The subsequent knots are either equal or greater than the previous ones. So it does satisfy my definitions, but it is a different knot vector than the one that we have been used to so far. What does this achieve? What it achieves for you is that if you look at this segment 1, 1, right? So this is x3, x4. Right? So let me just make some space here. Again, this is just for you to understand. So x3, x4, right? Now we know that nj1 is 1 only if xj less than or equal to u is less than xj plus 1. Right? So what this knot vector is telling you is that n31 will never be non-zero, right? It will always be 0 because I cannot find a u such that there is no u such that x3 is less than or equal to u is less than x4. This is something I cannot find. Okay, and therefore because n31 is 0, right, all the other subsequent basis functions are 0 in this interval, and therefore there is no definition possible. So these 3 basis functions that I need, namely p1, p2 and p3 in that interval, right? So in this interval, none of the basis functions are non-zero, and therefore p1, p2 and p3 will have 0 basis functions, and therefore the curve is not defined in that interval at all. And the same thing happens when you come to 2, 2, which corresponds to p3, p4, p5, and the same thing corresponds to 3, 3 when you come to p5, p6, p7. And therefore, you will get one segment between 0 and 1, another segment from 1 to 2, one from 2 to 3, and 3 to 4. So each of these will be that. So this is corresponding to 1, 2, 3, and 4, and 0. Both are the same. Okay, so that's the first segment, second segment, third segment, fourth segment. And the 7 got vanished because there is one 0 length segment here, here, and here, and therefore they get disappeared. So this knot vector is a slightly special type of knot vector. We call it the non-uniform knot vector. Okay, as opposed to the open uniform knot vector, which is this. So this representation for a circle with this input, this input, this input, and this input, right, will give me an exact arc of a circle. I mean, exact circle, or semicircle, or a 3/4 of a circle, or whatever you want. Right? And so I have this new curve where the knot vectors are non-uniform and the curve is rational, B-spline basis functions. Right? And so you get the most general form of the spline that you need, which is NURBS. Right? If my knot vector is open uniform, then I get the rest of the curves that we were studying so far, or even arcs of a circle less than 90 degrees. If all my weights are 1, I get the regular B-spline. And if my k is equal to n plus 1, I get the Bezier. Right? So this then is the most general form of the spline that we need to support in the CAD system. And by making appropriate choices as required, you can get each of the other types that we have studied so far. Right? N equals k plus 1, k equals n plus 1 will give you the Bezier. Weights not equal to 1 will give you rational, and knot vector, repeating but not arbitrary, only repeating will give you non-uniform. You need this to represent circles, right? You need this to represent arc of a circle less than 90 degrees, and you need this to make the number of control points independent of the degree. Okay. One last point. This picture I drew was with quadrants of 90 degrees each. Now, I can also do this with 3 segments. And while I say I can do this, I wish I had just downloaded a picture and shown you. Let me just try this. I always have a hard time drawing it. So roughly, if you see 120 and this is 90, 120. This is 180. So half of that will be 240 somewhere over here. Okay. So okay, I'm just going to clean this up. Oops, I did too much cleaning up, sorry. Okay, so now I have P0, P1, P2, P3, P4, P5, P6. Okay, so the angle subtended in this case, as I said, is 120 degrees. Therefore, what will be the H? This is 1. This will be cos of 60 degrees, right? And what is cos of 60 degrees? Is half, 1. And then this is half again, and 1. And this is half again. So I can define a circle with 9 control points. I can define a circle with 7 control points. I can define a circle with any sort of division of 360 degrees, right? So as many. So if I want divided by 60, I will get that many segments, right? 90 I got 4, 120 I got 3, 60 I will get 6, and so forth. Right? And all of them will be valid representations, except as somebody just said, you will have more control points. So if you have 9 you are not happy with, you can go to 7, right? And if you want more from 9, you can go to whatever number you get for the 60 degree included angle. Okay, so now that is the definitive solution for representing arbitrary curves and known curves, the NURBS, right? And the system will automatically choose appropriate simplifications or generalizations to achieve the representation you need. You need a circle, you will have non-uniform knot vectors. You need arc of a circle, then you use rational. And if you want Bezier, you will say k is equal to n plus 1. Okay. So that essentially completes everything that we wanted to cover in the case of curves, right? except one task, but I think I will do that along with surfaces, which is that there is another way for you to define a curve. So far we have studied two types of curves here. One purely arbitrary, which you define by moving these control points till you are satisfied with the shape. That is one way. The second is that you have a known shape, an expression or a mathematical equation, and then you construct the representation, which is what we have done today in the last class. The third one, what is the third variety or third way for you to construct or define curves? Can anybody have any thoughts? Is there any other way that you can think of where you can define the curve you want in a different way? Yeah.
Rotate a point about us.
Okay. So fine. What you say definitely is valid, but it sort of. So what is being mentioned here is that I rotate this point about an axis through the plane of the screen here, and that gives me something. But that is already known to you, no? What is that? It's always going to be fixed at as a circle. It can't be anything else, right? It can be a circle or parts of a circle.
Yes.
Yeah. So, I mean, yeah, you can try some of the other shapes, the involutes and all, but those are rather complex for you to construct also, So you're better off defining them some other way. One other way. You're pretty close here, though. You're pretty close here in what you suggested. So let me just elaborate what is happening here, right? So if you go by the suggestion your colleague made, right, what am I going to get? I'm going to get a point when, say, let's say I start rotating from this point here, right? The point is here and I start rotating in this direction. Therefore, for every theta, I'm going to get theta equal to 0, theta equals 0.5 degrees, maybe, I don't know, 2 degrees, 5 degrees, 4 degrees, 6 degrees, 8 degrees, 10 degrees, so forth. I mean, my spacing is bad, but you get the point, right? I get these points. That's what this construction will give you. Of course, the argument is that I can space this as fine as I want. I can get points for every 0.1 degrees, etc. But at the end of the day, I'm going to get a series of points. And actually, that is the input that we have not studied at all, which is that if my curve, it may not be a circle, it may be some arbitrary curve, but if it is defined as a series of points that lie on it. Right? So now I'm not trying to define the curve. I'm giving you points that lie on the curve, and I'm asking that you give me the CAD system to give me a representation for a curve. So this is a problem that is varyingly known as curve fitting or curve interpolation. And as I said, we will have to look at this problem. There is one implication of this that is important in CAD, so we need to look at this. But I just want to leave one point with you now before we move on to something else, which is that where do you get this input from? For a circle, yes, what your colleague suggested may work, right? That I can actually take a string with a pen or a pencil attached at the end of it and, move it along a circle and pick those points. But for a general arbitrary curve, where would I get these points from?
Sir, by tracing a point on a moving object.
By tracing a point on a
some moving objects, random.
Yes, you will get points there, but we are thinking of a shape here. You're right. I am looking for a locus of points. That is a set of points. I don't deny that. But if I just put a marker on an object that is moving in space and I get those points, that's what you're saying, right?
Yes, sir.
How is that defining a shape for me? And especially a shape that I'm interested in. See, it is not that I want to take any shape that comes. It is that I have a particular shape. I'm giving it to you in the form of points. So the question here is that given a particular shape, right? How do you get points on that shape? If you recollect the original workflow that we talked about in the case of these aerospace and the shipbuilding industries, etc. Remember, we said that the designer will design these curves, the plaster of model maker will come and fill them with the plaster of Paris. Then we said that the draftsman will go in and they'll actually measure points on these using dividers, protractors, and scales. That's where you get these points from. Okay, so you have a physical prototype or a physical model with you somewhere, and you measure these points of this physical prototype. Of course, in the olden days, it was very painful. You needed, people with gauges to mark a reference and then have protractors to sort of move, at fixed intervals and pick those points and measure the distances of those points along coordinate axes and marking those points on a sheet of paper. Right? But today, the same process has become very easy because of the availability of 3D scanners. Right? So I have an object which is lying on a table, and I have a gantry type device, on which I mount a source of light. As this, if it creates a line, and as the line moves, a point, and as the point moves along the curve, from the reflection of this light, I can calculate the Z coordinate, the X and Y coordinate. X coordinate comes from the location of the light on this gantry. And therefore, what would take days to pick points on a curve, now I can get it in less than a minute. Now, even more powerful is that if I don't have a point source, but I have a sheet or a line of light, then, of course, it is much faster. Then I'm scanning the entire surface in one go and getting points on the surface. But that's one source of input that we have to address, because it is part of the original statement that we had, right, of these people, that they are given a curve, but they are not actually given a curve. They are given points on the curve. And therefore, we need to find a curve from the points that lie on the curve. Okay, so we will need to address this problem. Actually, I just realized that we have spent far too much time on this topic today. I didn't plan on spending so much at all. We just have 4 minutes left. Okay, so let me then just finish this off before starting a new topic, right? So what is this problem now? So let's go back to your curve expression. Let's say a spline expression that I have, I equals 0 to n pi ni k of u. That's my expression. The only difference now is that I'm given a bunch of points QR, right? So this point is QR. And so my curve fitting problem then becomes one of, so here the unknown is this. So far that we were doing, these were all known, K was known, N was known, Nik was known, Pi was known, I find P given a U. Here, Q is known, a point on the curve is known. The basis functions, we have to see whether we know it or not, but the unknowns are Pi. I want to find these. And I have R such points, capital R such points. Right, so I go from 0 to capital R, so R plus 1 points, right? And each of those points must satisfy this equation. Correct? That's my problem that I need to solve. So this is my curve fitting or curve interpolation problem. Do I have everything I need? Pi, I don't know. Fine. What about N? Do we know N? we don't know n, right? It's something that has to be figured out. K, we don't know k either, right? But k, we know we have a good engineering choice, right? Without any issues, we can start with k equals 4. Unless you happen to know a priori that it is quadratic, in which case you can fix it to be 3. But in general, for some arbitrary curve points, points that come to you on an arbitrary curve, you are very safe assuming k to be equal to 4. Right? So the only thing left here then is n, and we'll just figure out how to pick n now. But other than that, once I know, assuming that you have also picked the value of n, then nik's are known. Okay. So then I'm only left with 1. And though this expression looks very complex, right? There is a summation and some basis functions and all are there. But what you must realize is that the unknown appears in a linear sense. So it's actually a linear system of equations. Right? You don't have to worry too much about it. MATLAB can solve it. Anybody can solve it for you. So what I'm going to do right now next is I'm going to write it in a matrix form, right? Where I replace the input single point as an array of points, and I write my summation in the form of a matrix, and I will just tell you what the terms mean, right? So this is Q. It's a vector of r+1 rows and 1 column. Okay, just a series of points. P is the other way around. You know, I have n+1 rows and 1 column. Right? So P, you all know how it will look like. It will be P0 all the way till Pn. N is the vector r+1 multiplied by n+1 columns. Right? So just so you have a feel. Okay, let me just leave it at a point where we can pick it up in the next class. So I'm just going to write down one of the rows, the rth row of n. Right, the rth row of n, the terms, it's a horizontal array. So the first term will be n01 of ur, n11 of, sorry, n0k, n1k of ur all the way till nnk of ur. And I have capital R types term in rows like this. Right? So that's the equation that I want to solve. Now, if I look at this matrix n, and here comes the first choice, if n is equal to r, right? Then this is very straightforward. Right? Because then P is nothing but n inverse of Q. That's it. And you're done. Right? You have an exact solution. You're done. Now, n equals r is possible if r is a small finite number, meaning if I give 10 points on the curve, then I can choose n to be 10 without difficulty, and I can solve this exactly, and I'm done with it. Now, those of you who have used CAD systems will note that in some CAD systems, actually in most CAD systems, you know, when you define a spline, you actually define it by picking points on the thing, and the system will actually generate a curve that looks like this on the fly. It is exactly solving this problem. Okay, as you keep adding points, it keeps changing n, computes the n matrix here, and inverts and solves for P and gets the curve. Okay, so that's one problem. It can be solved exactly. So the advantage here is that I get an exact solution. What do I mean by an exact solution? That each of these points lie exactly on the curve as you have input. But scanning, you know, implies this, right? Those of you who are familiar with scanning systems, right? The light can be sampled very rapidly. Right, in the sense that in every millisecond I can pick points on the curve as you're going from left to right, right? So if you're picking a point every millisecond and you're scanning this over a period of 5 seconds, right, then you have 5,000 points right there, right? And therefore, it is not at all possible that you're going to have a curve with 5,000 control points. That defeats the whole purpose. You want a concise representation. And therefore, we have now deal with the situation where R is much greater than N, which means that this is a rectangular matrix, not a square matrix. And therefore, I need a different way to find a solution. And I'm going to write down the solution. I don't expect you to sort of remember this, but the solution looks like this. P is equivalent to sorry, I drew the bracket at the wrong place. Okay. This is so basically I multiply both sides by n transpose. So n transpose n becomes a square matrix, so I can invert that and I get this as my solution. Again, you are not doing this. Some computer program is going to do this, so you don't have to worry about it. But the implication of this is that this solution is not exact. Unlike this. Okay, what it means then is that if I have these as my points, my curve will probably look like this. Okay. The only guarantee you get from this is that this solution minimizes the least square error. What does least square error mean? That if I take the distance between the point and the curve, square it and add it for all the points, no other solution can give me a smaller error than this. That's what this means. Okay. So that's what it is. I can do the curve fitting problem exactly if I have the luxury of choosing the control points to be the same as the input number of points. But that's a luxury. You know, it's only in manual input that you can expect this. But if I'm getting my input from a scan, then this is what will prevail. And there I'm only happy with the minimal least square error case. There are ways to improve this, right? But that's always you'll get only the least square, minimum least square error. Okay. I'll stop here and we'll pick it up on Monday. And I don't know if you have seen this notice from the academic section that there will be no contact this time. And so we will be planning the lab sessions possibly starting next week through online instruction only. And hopefully we can enable each of you to get access to the CAD system so that you can work on your own wherever you are and then turn it in and then we can do the evaluation from here. Okay, so that's the plan. We will release, or Monday, if possible, I will share a plan with you. But my bigger task is to sort of start the instructions on the CAD tools that you'll be using from next Wednesday. So I hope I'll be able to do that. And we will do it online, either 2 to 5 or 3 to 5, whichever way it is convenient to the people who want to come and give these instructions. Okay, I'll stop here. And as always, questions, I will pick it up at the beginning of the next class. Thank you very much.
Thank you, sir.
Thank you. Yeah.
Thank you.
Bye, sir.
Thank you, guys. Yeah, bye.
Thank you, sir.